So we are looking at a new rule for us. We're looking at indeterminate forms of limits. So kind of going back to the beginning of the semester where we got 0/0, and that was an indeterminate form, and we knew that didn't tell us anything about the limit, and we had to go back and manipulate it, be it either factoring, maybe getting rid of complex fractions, fractions within fractions. We just had to go back and manipulate it some way. So here is a rule that will help us if we get that indeterminate form 0/0, and it's called L'Hopital's rule. So the rule states the following. Suppose that f of a and g of a are equal to 0, that f and g are differentiable on an open interval I containing a, and that g prime of x is equal to 0 on I, and if x doesn't equal a, then we know that the limit as x approaches a of f of x over g of x, this is going to be the same thing as if we took the derivative of our numerator all over the derivative of our denominator. And that's assuming that the limit on the right-hand side of the equation, of this equation, exists. So I kind of want to go back to one of those special limits that we dealt with at the beginning of the semester. Recall when we looked at the limit as x approached 0 of sine of x all over x. We saw that that was equal to 1, and we proved that with using the sandwich theorem. So I want to show that we still get 1, but using L'Hopital's rule, which is a lot easier than going through and using the sandwich theorem. So first thing that you want to do is you want to make sure and show that you get in the form where you can use L'Hopital's rule. And so again, we're just going to do, when we're doing limits, first thing you always want to try is direct substitution. So we're going to go in here and we're going to do our direct substitution. And if we do that, we get sine of 0 all over 0. And recall sine of 0 is 0 all over 0. So that is our indeterminate form. And now, because of our L'Hopital's rule, we can use our rule. So I'm going to put out here that I'm using L'Hopital's rule. So LH. So I'm looking at the limit as h goes to 0. So I want to take the derivative of my numerator. So derivative of sine of x was cosine of x all over the derivative of my denominator, which is 1. And so now if I go do direct substitution, we get that this is cosine of 0 all over 1, which I don't have to write that. And I know that cosine of 0 is 1. And so we just showed that the limit as x approaches 0 of sine of x over x is 1 using L'Hopital's rule. So our next example in front of us is the limit as x approaches 0 of 8x squared all over the quantity cosine x and then minus 1. And that's all underneath in the denominator. Again, I noticed if I did direct substitution in here and I plugged in 0 wherever I got an x, I would have 8 times 0 squared is 0 in my numerator, all over cosine of 0, which is 1. So 1 minus 1 is also 0. So we have the indeterminate form of 0/0. So because of this, we can use L'Hopital's rule. And L'Hopital's rule says we're going to just take the derivative of the numerator divided by the derivative of the denominator, and then we're going to look at the limit. So I just want to make sure that you realize you're not using the quotient rule here when you're taking the derivative. Just derivative of the numerator divided by the derivative of the denominator. So if I look at the derivative of my numerator here, 8x squared, bringing down my power. So 2 times 8 is 16. Subtract 1 from my power, I get 16x. All over the derivative of cosine x. Well, the derivative of cosine x is negative sine x. And so now if we look at this and we plug in 0, guess what? We get 16 times 0, which is 0, all over negative sine of 0, and sine of 0 is 0. So we're getting that form again, 0 over 0. Sometimes you need to use L'Hopital's rule more than once. And so let's go again and apply L'Hopital's rule. So looking at the derivative of our new numerator 16x, taking that derivative gives us 16. And the derivative of negative sine x is negative cosine of x. And so now when we do direct substitution, we're not getting that indeterminate form anymore. We're getting that 16 over negative cosine of 0, which is negative 1. So this is equal to negative 16. So recall when we're looking at limits, as x is approaching 0, this function 8x squared all over cosine x minus 1, as x gets closer and closer to 0, our graph is getting closer and closer to the y value of negative 16. If we get something in the form infinity over infinity, L'Hopital's rule also works because we can manipulate that to get it in the form of 0 over 0. So let's just say that actually, let's not even look at this. Let's just show that that would be true. So let's say you had the limit as x is approaching some number a of some value f of x all over g of x. And you got that this was equal to infinity over infinity. So we talked about this being an indeterminate form in the beginning of the semester. And so this didn't tell us anything. And we wanted to manipulate this so that we could find the limit. Well, let's manipulate this by rewriting the form of that. If I rewrite this, this is the same thing as 1 over g of x, all divided by 1 over f of x. Think about it. Let's just show that on the side. If I had 1 over g of x divided by 1 over f of x, I can write it like this. And this is the same thing as 1 over g of x times f of x over 1. Okay, so that is the same thing that we had above, what we were taking the limit of. Recall, though, if you were taking the limit and we had something of 1 over, let's just say, f of x went to infinity, we saw that 1 over infinity, we saw that that goes to 0. So in this case over here, this would be saying, well, I know f of a goes to 0, infinity, and g of a goes to infinity. So this would be 1 over infinity divided by 1 over infinity, which is 0 over 0, which means that I can use L'Hopital's rule. So if we get in that form, infinity over infinity, we can use this rule too. I just showed why. So let's look at an example of that. So the next example in front of us is the limit as x is going to infinity of 2x cubed plus 3x all over x cubed plus x plus 1. So the directions in here says use L'Hopital's rules to evaluate this limit, then evaluate the limit using the method that we used at the beginning of the semester. Okay, so if we go in here and we plug in infinity wherever we saw an x, you can see that you get infinity over infinity. This here, again, is a indeterminate form, doesn't tell us anything. So let's go through and use L'Hopital's rule. So L'Hopital's rule says, okay, well, we're going to go through and we're going to take the derivative of the numerator. So the derivative of this numerator, derivative of 2x squared is 4x, plus the derivative of 3x is 3, all over the derivative of our denominator. So the derivative of our denominator, x cubed, is 3x squared, and the derivative of x is 1, and the derivative of our constant 1 is 0. So I notice again, if I go in and do direct substitution, I'm getting my indeterminate form of infinity over infinity again. So we want to go through, use L'Hopital's rule, and we're going to take the derivative of our new numerator. So the derivative of this 4x plus 3 is just 4, all over the derivative of our denominator. So derivative of 3x squared is 6x, and the derivative of 1 is 0. So now when we go through and we do our direct substitution, we're going to get the form of 4 over 6 times infinity, which is infinity. And we know a number over infinity, this goes to 0. Okay, so that was using L'Hopital's rule. In the past, when we were looking at limits as it went to infinity or negative infinity, and we got infinity over infinity, our trick was to multiply both the numerator and denominator by the variable to the highest power that's in the denominator, 1 over that. So multiplying this by a fancy one, I noticed that my degree in the denominator is 3. I'm going to multiply each term in my numerator by 1 over x cubed, and each term in my denominator by 1 over x cubed. So doing that, we have 2x squared all over x cubed reduces to 2 over x, plus 3x all over x cubed reduces to 3 over x squared, all divided by x cubed over x cubed is 1, plus x over x cubed is 1 over x squared, plus 1 times x cubed, 1 over x cubed. So now, as x is going off to infinity, any number over infinity goes to 0. So 2 over infinity goes to 0, 3 over infinity squared goes to 0, 1 over infinity goes to 0, 1 over infinity cubed goes to 0. And so what we're left with in our numerator is something that goes to 0 all over 1, which is equal to 0. So we can still do the same way that we did it in the past, or in this case, we can use L'Hopital's rule if you prefer. So our next example we have is the limit as x is approaching 1 on the right of 1 over x minus 1. And then that fraction is minus 1 over the natural log of x. If we go in here, when we plug in 1, we'll see that we're getting basically infinity over infinity. Or sorry, not infinity over infinity, infinity minus infinity. That is an indeterminate form, and so that doesn't tell me anything. And I want to manipulate it so that I can use L'Hopital's rule. So if you have two fractions, try rewriting it as a single fraction. So we need a common denominator here. You can see my least common denominator is equal to x minus 1 all times the natural log of x. And so rewriting this, looking at the limit as x is going approaching 1 on the right, getting my common denominator, that would give me a natural log of x times 1 all over the natural log of x times x minus 1. And then minus our second fraction, we're going to need to multiply both the top and bottom by x minus 1. X minus 1. Let's simplify that a little bit. Limit as x is approaching 1 on the right of the natural log of x minus x plus 1 all over the natural log of x times x minus 1. And so if we go in here now and we do our direct substitution, and we plug in 1 wherever we see an x, notice we get the natural log of 1 minus 1 plus 1 all over the natural log of 1 all times 1 minus 1. But the natural log of 1 is 0, so I have 0 minus 1 plus 1 gives me 0 in my numerator. All over the natural log of 1 is 0 times 0 is also 0 in the denominator. So now it's in the form that we can use L'Hopital's rule to help us evaluate this. So we want to go through, we want to use L'Hopital's rule. So I'm looking at the limit as x is approaching 1 on the right. And let's go back up here and let's differentiate our numerator. So remember the derivative of the natural log of x, that was 1 over x, minus the derivative of x is 1. Derivative of 1 is 0. All over. So when I take the derivative of my denominator, notice I have a product rule here. So I need to use my product rule, taking the derivative of the denominator. So if I take the derivative of the first piece, natural log of x, I'd have 1 over x times my second function, x minus 1, plus the natural log of x times the derivative of x minus 1, which is just 1. Let's see if I can clean this up a little bit. If I distribute that 1 over x here, then the limit as x is approaching 1 on the right of 1 over x minus 1 all over 1 over x times x is just 1 minus 1 over x times 1 is 1 over x plus the natural log of x. So it looks like I'm still getting that form of 0 over 0 when I plug in 1. Let me rewrite this a little bit before I go through and use L'Hopital's rule again. So I don't have to use the quotient rule and then take in the derivative of the numerator denominator. So remember 1 over x, we can rewrite. We can bring that up into the numerator and rewrite it as x to the negative 1 minus 1 all over 1 minus x to the negative 1 plus the natural log of x. So let's see if this helps us going back and taking the derivative, both of the numerator and denominator. Now, when we take the derivative of the numerator and the denominator, we don't have to worry about the quotient rule. So now again, using L'Hopital's rule, again, the limit as 1 approaches 1 on the right. So the derivative of x to the negative 1 power is negative x to the negative 2 power. Derivative of constant is 0. Derivative of constant in the denominator is 0. Let's bring down our power. So -1 times the negative in front is +1. X to the -2 power plus the derivative of the natural log of x, which is 1 over x. So looking at this, let's rewrite it a little bit. So I have -1 over x squared all over 1 over x squared plus 1 over x. So now if we do our direct substitution, it looks like we're not getting that form of 0 over 0 anymore. So doing that, I would get -1 over 1 all over 1 over 1 squared plus 1 over 1. 1 over 1 is 1, all over 1 plus 1 in our denominator. So we get that, looking at the limits of our function, we go to 1/2.
I think you forgot the negative sign on this numerator.
Ooh, on the numerator, thank you so much. So bringing down this negative right here, -1, this should have been -1/2. So our next example, limit as x is approaching 1 on the right of x, that x is raised to the power of 1 divided by x minus 1. So we have a problem here. We got 1 to infinity if we look at this, and that is an indeterminate form. If you have the variable in the exponent like that, one way to help you is to manipulate it and rewrite it. So recall back in algebra, because we're going to use properties of logs to bring this down, but recall that if you had e, the natural log of some function f of x, this is equal to f of x. And so let's assume right here that this is our whole function of f of x. And so let's rewrite this. The limit as x approaches 1 on the right of e to the natural log of x raised to the 1 over 1 or x minus 1 power. So I'm going to use properties of logs that says we can take our exponent of our argument and bring it down front of the natural log in this case. So I have the limit as x is approaching 1 on the right of e, that's raised to the 1 over x minus 1 natural log of x, which I can rewrite this a little bit. This is the same thing as a limit as x approaches 1 of e to the natural log of x all over x minus 1. Okay, because e is a continuous function, we can use rules of limits here and actually just take the limit of our numerator. So we have e raised to the limit as x is approaching 1 to the right of the natural log of x all over x minus 1. Through here, notice that our limit, when we plug in 1, wherever we see an x, we're going to get 0 over 0 for that limit. And so I can go back and I can use L'Hopital's rule on that limit. So e is still there. Write the limit as x is approaching 1 But now I'm taking the derivative of the natural log of x, which is 1 over x, divided by, and this is all, divided by x minus, derivative of x minus 1, which is 1. So looking at this, we have e equals a limit as x is approaching 1 on the right of really just 1 over x. And so if we do the direct substitution in that exponent, we're going to get the limit as x approaches 1 on the right of 1 over x is just 1. And so this is e to the first power, which is just e. So looking at another example that is going to give us an indeterminate form where we're going to have to manipulate it to use L'Hopital's. So if you have a limit as x is approaching 0 on the right of x squared times the natural log of x. So it'd be helpful if you remember what the natural log of x, the graph of that looks like. If you look at the graph, the natural log of x looks like the following. And so notice as we're approaching 0, on the right-hand side, that's shooting down to negative infinity. And so we're getting something like 0 times a negative infinity. And so if you get 0 times infinity or infinity times infinity or infinity minus infinity, these are indeterminate forms. Infinity raised to infinity power. There's just different indeterminate forms, and I'll pull up some I'll pull up some indeterminate forms in a minute after we go through this example. So we want to manipulate this so we can kind of rewrite it, maybe 0 over 0. And so I noticed that if I looked at this, let's see if we can manipulate this. How about limit as x goes to 0 of x squared all over 1 divided by the natural log of x. So that is exactly the same thing, because if I flip up when I'm dividing by 1 over the natural log of x, that would be x squared times the natural log of x. But now if I go in and I plug in 0 wherever I see an x, I get 0 divided by 1 over infinity, which is 0. So I get that indeterminate form, which I wanted, 0 over 0. And now that I get that form, now I can use L'Hopital's rule. I can go through, I can just take the derivative of my numerator. So derivative of x squared gives me 2x all over the derivative of my denominator. We might need to be a little bit careful here, because right now, if I took the derivative of my denominator, which I guess we can just do it that way, we need to use the quotient rule for that piece. So the derivative of my numerator 1 is 0 minus the derivative of natural log of x, which is 1 over x times 1, all over the natural log of x quantity squared. The limit as x is going to 0. This is not looking very pretty. Let's rewrite this. This is the same thing as saying 2x divided by, which is the same thing as multiplying by our reciprocal. So natural log quantity squared all over negative 1 over x. Which technically I can flip. So the limit as x is approaching 0. This is really 2x times the natural log of x quantity squared times the reciprocal of 1 over x, which is just x. Which did not look like it helped me any. Because this is going to give me 2x squared all times the natural log of x quantity squared. Okay, so that didn't work. So I'm guessing that I probably chose the wrong things. I chose it the wrong way. Let's look at it the opposite way. Instead of writing it with like this, let's try writing it like this. So limit as x is going to 0 of natural log of x all over 1 over x squared. So in this form, we're getting infinity over infinity, which is our indeterminate form. Let me just rewrite this a little bit. So limit as x is approaching 0 on the right of the natural log of x all over x to the negative 2 power. So now let's go through and take the derivative again. So bringing down the limit. So derivative of our numerator, ln of x is 1 over x, all divided by, let's bring our power down, negative 2x to the negative 3rd power. So limit as x is going to 0. So this is the same thing as 1 over x divided by negative 2 over x cubed. Looks like this might have worked. So limit as x is going to 0 to the right of 1 over x times the reciprocal, which would be x cubed over negative 2, which I notice simplifies. So limit as x goes to 0 on the right. Notice that x in the denominator cancels with the x cubed in my numerator, leaving me an x squared, and my numerator divided by negative 2. So now when I go through and I do my direct substitution, notice I'm not getting that indeterminate form of 0 over 0 anymore. I'm getting 0 squared over negative 2. Well, 0 over negative 2 is equal to 0. So if you have something with multiplication and it's not in that form, try manipulating it, rewriting one of those pieces as 1 over that function in the denominator. I noticed that what I chose, it was just going to continue to give me that loop where it wasn't going to start breaking things down. And so that's where I decided to go back and change what I had, how I written it in the first place. So it just looks like I made an error over here when I was taking the multiplying by the reciprocal of negative 1 over x. I should have brought the negative. That should have been negative x there, which brought a negative. That didn't help me at any, so I still had to go through the process that we did when we rewrote it in the other form. There are other indeterminate forms that you might see. You cannot use L'Hopital's rules when they're in this form unless you can manipulate it to be in the form of 0 over 0 or infinity over infinity. But those are other forms that you may see. There was one that I wanted to look at and show you using calculus that the limit as x is approaching 0. Let me just find it. Of 1 plus x raised to 1 over x, which show this is equal to e. Okay, so I have a problem. I'm going to plug in 0 in there, and I'm going to get 1 to infinity. 1 to infinity is one of those indeterminate forms. And so we want to go through, we want to manipulate this. I notice I have a variable in my exponent, so I'm going to manipulate this and rewrite it. So we're looking at the limit as x is approaching 0 of e raised to the natural log of this function. So 1 plus x raised to the 1 over x power. And now I can use my properties of logs to bring my exponent down in front of my natural log here. And so I have the limit as x is approaching 0 of e raised to the 1 over x natural log of 1 plus x. Or we can look at this as limit as x is approaching 0 of e raised to the natural log of 1 plus x all over x. And so as x is going to 0, we get 0 over 0 in our numerator. And so again, that's an indeterminate form. And we want to go back and manipulate this. Actually, that was not 0 to, that's 0 over 0, not 0 to the 0. So we can use rules of limits where we can look at e. We can take the limit as x is approaching 0 of our natural log of 1 plus x all over x. So using L'Hopital's rule here, we have e to the limit as x is approaching 0. The derivative of our numerator, well, the derivative of a natural log is 1 over what you're taking the natural log of, 1 plus x, times the derivative of the inside, which is just 1, all divided by the derivative of x, which is 1. So now when we go through, when we do direct substitution, we have e raised to the, going in and plugging in 0 where you see an x, we get 1 over 1 power, which is equal to e. We showed that the limit as x approaches 0 of 1 plus x, all raised to the 1 over x, was equal to e using L'Hopital's rule.
Hey, could you explain again, like in the very beginning, if we were to just plug in 0 for x, what indeterminate form would that be?
If we, in the beginning, just plugged in x, we would have gotten here that the limit, well, let's just go back in and plug x. We plugging in 0 for x, we have 1 plus 0, and then we have 1 over 0. But remember, 1 over 0 is infinity. So we have 1 to the infinity form. And something in the form of 1 to infinity is an indeterminate form. So it doesn't tell us anything. We got to go back and manipulate it.
Okay, thank you.
Yeah.